Welcome to another edition of Statistics Heuristics. In this episode, we may not discuss aspects of normal distribution from A to Z, but we will discuss the Z to begin. In fact, we will dive into Learning Target 2.1.2 of the Starnes, Tabor, and Wilcox Statistics and Probability 4th edition, which asks the student to find and interpret a standardized, or Z-score, in a distribution of quantitative data. Learning Target 2.1.2. Find and interpret a standardized, or Z-score, in a distribution of quantitative data. To start, let's define a distribution of quantitative data. That's a fancy phrase to stand for the numbers making up a sample, that is, the data. All data here is from Census at School, which compiles survey information from U.S. students. In this lesson, we will be working with two sets of data from 39 students who attended Maryland high schools when they completed the survey. The same 39 students responded to one question about their height and one question about their respective performances on a memory test, along with other responses. In cartoons, a Z might represent a snore, but the Z-score in statistics is not a bore, and it represents how near or far a number falls as compared to the average or mean. Think of this example. If you bomb a test, you may be able to calculate a Z-score to show a parent that your grade was close to the average test score in your dataset or class. The Z-score results in an answer showing how many deviations or differences you are away from the average on a scale from about 0 to 3, or really at most 3.5 derivations away from the mean or average, either above it or below it. How do we calculate the Z-score? First, let's take one of our data sets. Using the 39 answers from the scores in the memory test, we use the Staplet found at www.staplet.com, input the data, and arrive at a summary analysis as follows. On the Staplet, click on the choice for one quantitative variable single group because you are only looking at one set of data here, the memory test scores. I named the dataset variable as Maryland high school students' memory test scores and clicked on the drop-down for raw data and entered the memory test scores, and then I clicked Run Analysis. The two crucial pieces for Z-score analysis are mean and SD, or standard deviation. While Z-score generally tells you the distance of an individual score from the mean in a dataset, the standard deviation tells you how clustered around a mean the entire group of numbers are. Now that we have these statistics, we can use some of them to find the Z-score. You must memorize this formula. It is Z equals value minus mean divided by SD, or standard deviation. Let's use a sample test score from the memory data to demonstrate a Z-score. Suppose you received a score of 37 on the memory test. Where does that place you compared to the average? Just how different or deviant are you from the average or mean? Here, we plug the 37 individual memory test score into the formula using the mean and standard deviation that was determined by the Staplet. Let's plug into the formula. V equals your test value of 37, and the mean in the summary statistics box is 42.077, and the standard deviation equals 10.732. 37 minus 42.077, all divided by 10.732, equals a z-score of negative 0.473071189, which we generally round to 2 or 3 values, so the z-score here is negative 0.47 deviations from the mean. How do we interpret z-score data? Realize that if something is negative, it does not necessarily mean bad. It just means that the value, your memory test score here, is below the mean. There are times where you might want a negative below the mean z-score, such as when you are calculating a BMI body mass index, right? A positive z-score means you are above the average or mean, and the bigger the number, the farther away you are from the mean. So here, your memory test score of 37 is negative 0.47, so it is 0.47 deviation below the mean memory score of 42.077 for this set of data, and that is how you would write an interpretation. You performed below the average or mean. What can we do with these z-scores beside understanding the individual score's distance from the mean? The answer is we can use them in calculations to see if a distribution of quantitative or number data is what we call normal. But first, we have to understand the empirical rule and the concept of a so-called normal distribution, which gets to learning target 2.4.1. Learning Target 2.4.1 asks students to use the empirical rule to estimate the proportion of values in a specified interval in a normal distribution. First, a normal curve, according to the Starnes text, is one that can be drawn to a line with a histogram and is described as symmetric, with one peak and a bell shape. Its mean aligns with the center mean, or mu, at the same location on the number line as the midpoint of the curve, and is matched by the median in the same location. The empirical rule is a phenomenon only applying to normal distributions, and the normal distributions will typically approximate the values of the empirical rule. The rule holds that once the mean and the standard deviation is determined from the statistics box we derive from Staplet, approximately 68% of the data will fall within one standard deviation below and above the mean, 95% of the data values will fall between 2 times the standard deviations below and above the mean, and 99.7% of the data values will fall between 3 times the standard deviation below and above the mean. It is just something that must be memorized, and it is also called the 68, 95, 99.7 rule. If you have this normal distribution that follows the 68, 95, 99.7 rule, you can easily estimate the proportion of values in a specific interval under the normal distribution curve if the intervals fall within specific standard deviations from the mean. Let's use the second set of our Maryland High School student data about height to demonstrate this process. The Maryland height data can first be entered in the Staplet under the qualitative variable choice, single group. We would then click Normal Distribution, put in the descriptive title of Maryland High School Heights, enter the data separated by a space or a comma, and then begin the analysis. We obtain the summary statistics box that gives us what we need to plot a curve. Here, the mean is 171.046, and the standard deviation is 9.301. We also could use the general analyzed data portion of the Staplet to see the general histogram shape of a data set if on the graph portion of the one quantitative variable single group page the histogram choice was clicked. If the histogram looked nothing like a bell curve and had, for instance, multiple peaks, it would be pretty clear that this was not a normal distribution of data, which has a distinctive hill shape. Here, there is a single peak, there is a sense of balance about it, and we can proceed to examine intervals of standard deviation under the normal distribution curve. Additionally, after obtaining the data from U.S. Census at School, we were able to plug it into the site Social Science Statistics Test of Normality, which indicates quickly whether or not the data is approximately normal, such as that it was capable of creating a bell curve when plotted. The height data of Maryland High School students did, in fact, follow a normal curve, so we can use data from the curve to show regular intervals. So let's draw a normal distribution and illustrate what I'm talking about. This slide reflects how to use the Staplet to plot a normal curve. The mean and standard deviation were found by using the Staplet to analyze the data generally to come up with the summary statistics box. By then moving to the probability section and clicking on normal distributions, the mean and standard deviation were input and the normal distribution was plotted. The middle number here is 171.046, which is both the mean and the median under the normal curve. Marking the standard deviation intervals on the curve makes it easier to understand how an estimate would be made of the proportion of values in a specified interval in a normal distribution, as noted in Learning Target 2.4.1. These results came from the Staplet, and the standard deviations were noted. Returning to the empirical rule, from -1 to +1 standard deviation from the mean, between 161.75 to 180.35, we should find approximately 68% of the data in this height distribution, 34% on each side. Between the values of 143.14 to the left of the mean and 198.95 to the right, which is between negative and positive standard deviations of 2, we should approximate 99.7 of all of the data of the heights from this distribution. Now that we have these values, we can divide up the distribution under the curve on the interval lines of plus or minus standard deviations 1 through 3 to estimate a proportion of values that use these intervals as boundaries. Suppose we wanted to find the proportion of values of the heights of the Maryland students that fell within certain marked standard deviation intervals, like finding the proportion of students falling between the lower second deviation value from the mean equaling 152.44 to one standard deviation to the right of the mean, which equals 180.35. We could shade these amounts on the curve to add up the individual pieces of the puzzle. The percentage value from -1 to +1 standard deviation is shaded, and that is 68% of the area under the curve. The area under the curve from the mean to -2 is half of 95, or 47.5. Since we already have accounted for 34% of that amount by figuring out mean to -1 SD at 34%, subtract that 34% from the distance between the mean and the -2. Ultimately, add up the 34% representing the mean to +1 SD, the 34% of the mean to -1 SD, and 13.5% constituting the proportion from -1 SD to -2 SD. 34% plus 34% plus 13.5% equals 81.5%, which we translate to a proportion of 0.815, considering that the entire area under a normal curve is 1.0. That brings us to another learning target 2.4.3, which asks the student to use graphical and numerical evidence to determine if a distribution of quantitative data is approximately normal. Note, this cannot be done just by looking and seeing a nice distribution in the form of a histogram outline that is like a hill. Instead, you have to see if approximately 68% of the data falls within plus or minus 1 standard deviation, 95% of the data falls within plus or minus 2 standard deviations, and if 99.7% of the data falls within 3 deviations. Looking at the Maryland height data, between plus or minus 1 standard deviation, you have 161.75 to 180.35 centimeters. There are 29 out of 39, or 0.74 values between this interval. Between plus or minus 2 standard deviations, you have between 152.44 to 189.65 centimeters. And there are 38 out of 39, or 0.974 values in this interval. Between plus or minus 3 standard deviations, you have between 143.14 to 198.95 centimeters, and there are 1.00 values in this interval. These values in real life approximate the 68 to 95 to 99.7 rule. Comparing the memory task data, there is a different proportion in each interval of standard deviation. Based on the previous statistics summary of this data distribution, we saw a mean of 42.077 and a standard deviation of 10.732. Using the same method of calculation for the memory test data, we see between plus and minus 1 deviation, you have 31.345 to 52.739, so there are 34 out of 39, or 0.87 values in this interval. Between plus or minus 2 standard deviations, you have between 20.613 to 63.471, and there are 37 out of 39 values, or 0.95 values in this interval. Between plus or minus 3 standard deviations, you have between 9.881 to 74.203, and there are 37 out of 39, or 0.95 values in this interval. This does not represent an example of the 68, 95, 99.7 rule, and therefore is not approximately normal distribution. Learning target 2.5.1 asks the student to work with a normally distributed data set to find the proportion of values to the left of the boundary. This is simply accomplished using the Staplet once you have figured out a value's z-score. To find a proportion under a normal curve to the left of the boundary means finding the proportion of the area under the curve that is less than the boundary. Assuming that this is not a boundary on the standard deviation interval, a z-value must be calculated to act as the new boundary starting point. Here the example asks what proportion under the normal curve of the Maryland height data is to the left of or less than the 175 centimeters. To establish the boundary or z-score for the 175 centimeters, use the previously calculated mean of 171.046 and the standard deviation of 9.301. Take the value of 175 minus the mean of 171.046 and then divide by the standard deviation of 9.301, which yields a z-score of 0.425. This will then be plugged into the Staplet to find a proportion to the left of the calculated 0.425 z-score boundary. As seen here, once the z-score for 175 centimeters using the Maryland height data is calculated, the Staplet manipulation is simple. On the Staplet site, click under Probability and then under the hyperlink for normal distribution. Because normal distributions are basically alike, enter 0 for the mean and 1 for the standard deviations. Enter Plot This and the curve will pop up. Click on the Calculate Area to the left of the boundary and input the z-score calculator for the 175 centimeters value. The proportion under the curve to the left or less than or equal to 175 centimeters under this normal distribution is about 2/3 of the area under the graph at 66.46%, or a proportion of 0.665. Learning target 2.6.1. Find the value that corresponds to a given percentile in a normal distribution. Finally, it is possible under Learning Target 2.6.1 to use a Staplet to find the value that corresponds to a given percentile in a normal distribution. What if we knew the percentage accounted for under a normal distribution under a normal curve and wanted to know the value for the boundary representing a percentage? And let's say we want to know what value is at a boundary to 75% of the area under the normal curve. What is the approach? The answer is start with Staplet, obtain the z-score, and plug into the usual z-score formula, solving for the missing value. In this case, under Probability and Normal Distribution, click on the drop-down bar to choose this operation of calculate a value corresponding to an area. Enter 0 for the mean and 1 for the standard deviation. The plot distribution will pop up, and we may choose to find the 75th percentile for the Heights dataset by choosing the left tail boundary in an area of 0.75. Click on Calculate Value, which produces a z-score of 0.674. This will be used in the next calculations to reach the value. Once we obtain the z-score value from the given percentage, it is simple to use the standard z-score formula with the Maryland height data and mean known, so that everything is plugged in except the unknown value. The unstandardized value ultimately arrived at this case in x equals 177.31 centimeters.